Welcome back, everybody. This is our second session in JEE Mains previous year questions for chapter Magnetism and Matter. Before this video, we have made one video in this series, and that video can be found on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So, if some of your friends are preparing for the NEET, then you can guide them through that playlist also. And if you find these videos useful, then do press the like button, share them, subscribe to our channel. Your share and subscribe helps a lot. And if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. In the previous one, we completed up to question 5. This was the last one. And today we will go further. A magnetic dipole is acted by two magnetic fields which are inclined to each other at angle of 75 degree. So we have two magnetic fields inclined to each other. Suppose this is first magnetic field and this is second magnetic field. One of the fields has magnitude 15 millitesla. Dipole attains stable equilibrium at angle 30 degree with this field. So suppose this is our dipole and it attains equilibrium at angle 30 degree with 15 millitesla field, and we know that total angle between these two fields b1 and b2 is 75. So angle between dipole and the second field will be 45 degree. The magnitude of the other field we have to find out here, and this dipole is in equilibrium. So in equilibrium means total torque on this dipole is zero. So torque net is zero here, and net torque will be zero. So let us write down the net value of net torque, and this is suppose M. So our net torque will be M cross B1 plus M cross B2, and for equilibrium this has to be 0. Now, when we take cross product, we know we have to take angle in the counterclockwise direction. So when we looking for M cross B1, cross product M and B1, so we have to start measuring angle from the M and start go up to the B1. So angle between M and B1 will be this. That will be 180 minus 30. Angle between M and B1 will be 180 minus 30. So here we will have magnitude of M, B1 sine of 180 minus 30 plus, for second scenario, M and B2, angle between M and B2, we will start from M in the counterclockwise direction. So this will be the angle. So that is 45, that is known to us. So M B2 sine of 45 is equal to 0. Now sine 180 minus theta will be negative. Sorry, it will be 360 minus theta. And 360 minus 30 will be in the fourth quadrant, and in the fourth quadrant sine is negative and cos is positive. So it will be minus mb sine theta or sine 30 plus mb2 sine of 45 is equal to 0. Equating both of these, m taking m common and cancelling it. So we will have b1 sine of 30 is equal to b2 sine of 45. Value of b1 is 15 millitesla into sine of 30 is half, and sine 45 will come here, will be 1 by root 2. So root 2 come on top, and this is B2 for us. So it will be effectively 15 into 10 raised to power minus 3 divided by root 2. And solving this, we will get 10.63 into 10 raised to power minus 3. That will be nearly equal to 11.10 raised to power minus 3, or 11 millitesla. That is asked in the question, that in millitesla it is equal to. So option B will be the right answer here. Let's move to next one. A 25 centimeter long solenoid has a radius, total number of turns, current is given. If it is equivalent to a magnet of same size of magnetization m, magnetic moment per unit volume, then we have to find the value of m. So length is given to us 25 centimeter, and number of turns, here it is capital N. Small n is the number of turns per unit length. Here it is total number of turns, so that is 500. Current is given to us, that is 15 ampere. So first, let's find out this value small n. It is the number of tons per unit meter. So 500 divided by length in meter, that will be 25 by 100. So it is equal to 2000. Now we have the value of n, we have the value of I. So using this, we can find out value of magnetic field produced. And here we have to find out magnetic moment per unit volume. So magnetic moment is m. Here it is denoted by magnet. So magnetic moment, we know that is n times I times a, and divided by volume. Volume will be area into length. So a get cancelled here. This n is the capital N, not the small n. Small n is used when we calculate the magnetic field due to solenoid. Here small n is used, and when we are discussing about the magnetic moment, then we take the actual amount of turns. So a get cancelled, and we are left with Ni by L. N is 500, current is 15, length is 25 centimeters, so 25 by 100. So it will go 4. So 2000 into 15. So that will be 6. I think that will be 20 into 15. That will be 300 into these two zeros. So that will be 3 into 10, 4. That is option C for us. Moving to the next one. A bar magnet of length 6 centimeter has magnetic moment is given. Find the strength of the magnetic field at a distance 200 centimeter from the center of magnetic along the equatorial line. So suppose this is our magnet. We have to find magnetic field along equatorial line, means this one. Along this line we have to find magnetic field. And we know along this line value of magnetic field is given by mu naught by 4 pi m divided by, suppose this is distance d, so dq. That's the value on equatorial. So mu naught by 4 pi is 10 raised to power minus 7. Value of m is already mentioned at 4. Now coming to the distance. Now this distance is depend if this value is very small. Suppose this is a and this is x. This is x, and this is actually the value of distance t. Now, if x is very large as compared to a, then we approximate it is equal to x. And if both of these are comparable, then we can take their, we can use Pythagoras theorem here. Now, here it is mentioned that value of x, distance from the center of the magnet, it is 200 centimeter, and length of the magnet is 6 centimeter. So value of a will be half of that, that is 3 centimeter. So we can see from here that x is a is very small as compared to x, so we will ignore it. So we will have uh, uh, d is equal to 2 meter and cube of that. So that will be 4 by 8 or zero point 0.5 into 10 raised to power minus 7 or 5 into 10 raised to power minus 8. Option C will be the right answer. Let's move to next question. A thin circular disk of radius r is uniformly charged with density sigma greater than 0 per unit area. The disk rotates about its axis with uniform angular speed omega. The magnetic moment of the disk. So we have to find magnetic moment of the disk, and for this type of question can be solved in two ways. Let's start one with the simpler, and then we will use the normal method. So suppose this is our disk. This is our disk, and let's draw two thick surfaces here. This is the first one, and this is the second one. Let's change its color. So we have an orange disk, and on that disk we consider two thin small elements. Now assume thickness of both of these is dx. For this also dx and for this also dx. And distance of this one is, we can say, x, and distance of this one is z. So area of the first one, dA, area of the element at x distance will be 2 pi x dx, and area of the element at distance z will be 2 pi z dx. We assume the thickness of both of these elements is same. Now, if we compare both of these areas, we can easily say d of any area of az will be greater than area of ax. Why? Because value of z is greater as compared to value of x. And if value of area at z is greater, then as density is uniform, charge density is uniform equal to sigma, then we can say charge on this element z will be greater than charge on this element x. Means, although it is given that charge density is constant, but amount of the charge on the small elements which we are going to consider here for to solve this question is different, is variable. So we cannot directly solve this question. So either we have to use integration or we have to use gyromagnetic ratio method. So first we will use the gyromagnetic ratio method. In that method, we know that for any type of charge distribution, any type of rotating body, we know that magnetic moment per unit angular momentum, magnetic moment divided by the angular momentum of the body, is given by the charge on that body divided by twice of its mass. And here it does not matter how this charge is distributed. Only thing matter is that there is some charge on the body. Now, charge on the body will be surface charge density sigma times the area, that is pi r square. And here it is thin disk. That's why we are taking area pi r square. If it have been a thick disk, then area will be 2 pi r square. In thin disk, we assume that same charge is distributed on the upper and the lower surfaces. That's why we take the only one side area pi r square. So from this mu by L, as this is disk and it is rotating about its center, then moment of inertia of a disk that is rotating about its center will be L is equal to I omega, and here I is moment of inertia, that will be half mr square into omega. So mu by mr square omega divided by 2 is equal to charge, that is sigma pi r square divided by the twice of mass. So mass get cancelled and we have mu is equal to sigma pi r square omega by 2 into 2, 4. That is option C for us. And now let us use solve it by the integration method. For that we have to consider a small element, which we already have drawn two elements here. So let's use one of them and delete one. So here it is. Delete it. So what we consider here, again, charge density is given. Let us consider a small element of thickness dx at distance x from the center. So area of this small element dAx will be 2 pi x into dx. Now charge of this small element will be area into charge density, that is sigma. So sigma 2 pi x into dx. Now we have been given rotation frequency, that this disk is rotating omega. Let me check. Angular speed is given omega. If angular speed is given to be omega, then we know omega is equal to 2 pi into frequency, and frequency comes out to be omega by 2 pi. And why we are calculating a frequency? Because this is the number of times this frequency gives us rotation per second. This is the number of rotation of a disk per second, and as disk is rotating that much times per second, that charge is also rotating that much times per second. So when we have to calculate the, we can say, current, then total amount of charge rotating per second or flowing per second will be number of rotation multiplied by the charge in one rotation. So di, that is the current flowing per unit time or per unit second, that will be the number of rotation multiplied by the charge in one rotation divided by the time, that is 1 second. So it will be omega by 2 pi sigma 2 pi x into dx. 2 pi get cancelled and we have sigma omega x dx. This is the value of di. Now magnetic moment. Coming to the magnetic moment is current times the area. So we have area A and current as di. Now here we have two types of area. First, this was the area of the element only. This was the area of the element only, or the thicker part, or we can say this, if this color is, suppose this is pink color, then dA is the area of the pink part only. But whenever we calculate magnetic moment, the area we take, the area inside the loop, this area is area inside the loop in case of magnetic moment. So here dm will be area inside the loop is pi times the radius, that is x, so pi x square into dx or di. So pi x square sigma omega x dx. So it will be sigma omega pi x cube dx. And now integrating it from 0 to radius r, 0 to radius r, we will have sigma omega pi x4 by 4, putting the value radius r, so r4 by 4. So again the same result. Okay, one thing we missed there, it is r4, r square into r square, r4. So in by both of the methods we get the same answer. So these are the two possible ways which you can solve this question. Let's move to the next one. A magnetic needle is kept in a non-uniform magnetic field it experiences. So we know that torque is given by m cross b, and force is given by magnetic dipole moment into dp by dz, where it is the variation of the field. As it is, we easily can see the from the expressions that torque will be there whatever value of the p. If magnetic field is present, then torque will be there. It is uniform or uniform, non-uniform, it does not matter. So torque will be there. And if it magnetic field is non-uniform, means we will have some value of this variation of this gradient. And if we have some value of this gradient, means force will also be there. So both force and torque will be there in case of non-uniform magnetic field. So option D will be the right answer. And if field is uniform, then force will not be there, only torque will be there. Let's move to next one. The length of a magnet is large as compared to its width and uh, breadth. The time period of the oscillation in the vibration magnetometer is 2 seconds. Magnet is cut along its length into 3 equal parts, and these 3 parts are placed on one over each other like poles together, with their like pole together. The time period of this combination will be. So we have to find out time period of this combination. So initially we have a large magnet. Suppose its length is L and its breadth and width are very small compared to, so we neglect them. Now it is broken into three pieces, L by 3, L by 3 and L by 3, of length L by 3. Now assume pole strength of this magnet before breaking was M. Now we know that when we break the magnet, pole strength does not change. So again, pole strength stays M, pole strength stays M, and pole strength stays M. So now we can say total dipole moment of this magnet was M times L. For this magnet, these small pieces, we have ML by 3, ML by 3, and ML by 3. And as mentioned that we put these parts on each other such like their poles, their like poles are together. So we put them such that their like poles are together. So suppose this was north pole, this was south pole. So for them this was north south, north south, north south. So now all of the north poles are aligned, no, all of the south poles are aligned. So their magnetic moments will be added. and total magnetic moment will be ml by 3 plus ml by 3 plus ml by 3. So again we get the magnetic moment L. So from going this configuration to this configuration, magnetic moment, magnetic dipole moment has not been changed. But if we write the formula for a period of oscillation in a magnetometer, that is given by T is equal to 2 pi under root I, where I is the moment of inertia, divided by mp. It is actually m dot p. So now in this case, moment of inertia, we can say I1 is equal to ml square by 3. This is like the moment of inertia, oh sorry, ml square by 12. Moment of inertia of a rod. And now when we break rods into, when we break, we convert this configuration into this configuration, then we have where, okay, one thing which we have to correct here, we have to correct for the mass, because small m is already taken by us as pole strength, so we have to take capital M here. Small m is already taken as a pole strength, so mass will be taken by capital M, that we need to correct. So capital M is the mass. Now when we convert the when we break or split this rod into three equal pieces, so mass of each piece is capital M by 3 and its length is L by 3. So moment of inertia about the center of one piece, that will be m L square, that is L by 3 divided by 12. So it will be m L square, 3 square, 9 into 3, 27. So 27 into 12. And we have three rods aligned equally each other, so, with parallelly each other, means their moment of inertia will be added. So new moment of inertia, that is I2, will be 3 times of this value, and it will be ml square divided by 9 into 12. We just multiplied it by 3. And we can say it is ml square by 12 is the I1, so I2 is I1 by 3. So now we have the value of moment of inertia, magnetic field is same as it is, and pole strength is also the same, because we just calculated that, as we are putting them in such that their poles are inclined with each other. So pole strength, sorry, not pole strength, total magnetic dipole will not change. So if we divide, then T by T dash, then all the variables, 2 pi is same, m is same, b is same, only I has been changed, so it will be I1 by I2, and I1 by I2 is 9, so I1 by I2 is 9, so T is 2, T dash, it is 3, so value of T dash comes out to be 2 by 3 second. Let's move to the next one. A magnetic needle lying parallel to magnetic field requires W unit of work to turn it through 60 degrees. The torque needed to maintain the needle in this position will be. So we have a magnetic needle. Suppose this is magnetic needle, and initially it is parallel to the magnetic field. So this is, we can say, magnetic field direction, and it is the direction of magnetic dipole moment of the needle, and both are in parallel with each other. So initial angle, that is theta, is 0, so initial potential energy will be minus mb cos 0, so cos 0 is 1. Now, if we rotate it through 60 degree, then magnetic moment will also rotate by 60 degree, or angle between M and B becomes 60 degree. So potential energy final will be minus MB cos 60. Cos 60 is half. So it will be minus MB by 2. And work done here will be change in potential energy final minus initial. So minus MB by 2, negative, negative, positive, plus MB. So it will be MB by 2. So it is given that W is equal to MB by 2. We will use this expression in the form of torque. So it is requested to find the torque needed to maintain the needle in this position, and in what position, where angle is equal to 60 degree. So torque will be M cross B, or MB sine 60. Sine 60 is root 3 by 2. So root 3 by 2. Now from this we can say MB is equal to twice of W. So MB is equal to twice of W by root 3 into root 3 by 2, or torque is W3. That is option A for us. So with this, we end this video here. Hopefully whatever we have covered till now is helpful to you. Again, if you find this video useful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.